So let's try to identify what information is in the material strength tensor, capital E. Well, we know that essentially that tensor informs about variation of angles and distances of particles whose relative position is known at the reference configuration. It provides the variation of distances and angles of these particles at the current configuration. What is specifically informed by this term? You know that the strength tensor, when we have a certain reference configuration, the system of coordinates, when we have this Cartesian system of coordinates, can be expressed in terms of its components, so it would have those components. Look, that it can be written as Exx or E11, Exy or E12, etc. So we use both notations indistinctly. But now, look that they are symmetric, so that would be Eyx, but I call them Exy because I know they are symmetric. This would be E21, but I know that they are symmetric, so I call that E12, and this E12, so the same, and so on. So I want to identify what is specifically the information contained in any of these terms, these components of the strength tensor. So let's do some exercises to see what can be obtained. For instance, let's consider at the reference configuration two particles, but they are oriented in the direction of the first Cartesian axis. So it's two particles that are oriented in the direction T1, which coincides with E1. E1 is the first element of the basis. So the component of the T1, which is the unit tensor, is 1, 0, 0. Okay? So differential of x, in that case, would be differential of capital S, which is the length of this segment, times 1, 0, 0. So differential of x would be a vector whose first component is differential of S, the second component in that direction is 0, and the third component is 0. So this is differential of x. Well, what is the stretch corresponding to that direction? Well, we go to the formula, we go to the form, and then we obtain that the stretch is computed as the square root of 1 plus 2 t times e times t. Look, t times e times t means multiplying, for instance, this product is a matrix times a vector, which implies multiplying this, the matrix, times a column vector, which is exactly t, which is differential of S, 1, 0, 0. Oh, sorry, T1, 1, 0, 0, okay? And then I have to multiply the result, which is a vector, times square root of another vector. Times the dot product of the same vector. So to do that, I place the first vector in a column, so I first T1 transposed, and then I multiply by the vector which corresponds to that, which is what provides the scalar product of two vectors. Recall, the product of this is a vector. And to multiply this vector by another vector, I just place the first in a column and then multiply by the second, which is the result of that. But finally, that product can be expressed in that way. I have to do these matrix operations. This matrix times that, and the result is that. Can anyone anticipate what would be the result? It's relatively easy. Look, this is 1, 0, 0. So when I multiply this matrix times this vector, I will obtain the first column of this matrix, right? First, for instance, when I want to obtain the first column of this product is this times this. But this times this is E11 times 1 plus E12 times 0 times E13 times 0. So this is this E11. The second column would be that 1 times that 1 plus this times this plus this, so it will be epsilon 2. Sorry. In other words, multiplication of this times this gives the first column of this. And the multiplication of the first column times this is 1 times E11 plus 0 times 0 plus 0 plus 0. So the final result is E11. Okay? Easy to obtain. So, finally, that result in that case is square root of 1 plus 2e11. So, look, what I've done. The stretch of a segment that is placed in the reference configuration in the x1 direction can be obtained just by using that information. In other words, that term of the strain tensor informs about the stretch of segments which are oriented in the direction x1. Okay? So if I know this term in a given point, I know the stretch of segments oriented in the x1 or x direction. Okay? Of course, I could do the same for now taking T2 to or T1 0, 1, 0, so segments placed in that direction, and I would obtain, just by extension, that the stretch of segments placed in the x2 directions would be square root of 1 plus 2 plus, what would be here? If I'm talking about the second direction, e to 2. So that would be e to 2. So the important information is that e to 2 contains the information of stretches. So increase of length of segments in the x2 direction. And the same we can see of e33. Okay? So finally we can summarize that saying the stretch in the x direction is given by that, or the unit elongation in the first direction, so the increment is which is lambda x plus 1 is that expression. In any case, the stretches and the unit elongations in the x direction, in the reference configuration, is contained in this segment here. The stretches and elongations in the y direction is contained in this term here. And the stretch or elongations in segments in the z directions is contained in that segment. So, the summary is the elements of the diagonal of the strain tensor contain information through these formulas here, contain information about what? About the stretches or unit elongation of segments respectively in the x, y, and z direction. Okay? That is what these strains are called longitudinal strains. Longitudinal strains. In engineering language, we call that longitudinal strains because they inform of stretching of longitudinal directions in the axis. They are called longitudinal strains. Okay? Right? They are directly, the strains, almost directly, just through these operations, are typically unit elongations. Okay? Let's now wonder what is the final angle of two segments around in a neighborhood of a particle P, in an infinitesimal neighborhood of a particle P, two segments defined by Q and R who are oriented with respect to P, Q in the direction of x1 and R in the direction of x2. Okay? So, in that case, I have that T1 is 1, 0, 0 and T2 is 0, 1, 0. Okay? That's something that I can know in advance. So after the formation, these particles move to that position. P goes to P prime, Q moves to Q prime, to Q prime, and R moves to R prime. And they form another angle. I don't know what this angle is. I know this angle. How much is this angle? Before the formations, pi over 2, 90 degrees. That's what we call capital Txy, which is pi over 2. But this angle theta, which I will call T small t xy, is in principle unknown. But I want to know it. How do I know it? Well, I use this formula. This formula says that the cosinus of this angle can be obtained just by doing this operation. Okay? So this operation maybe, well, this part I know. What is this part? This part is the operation I've done before. This is 1 plus 2 and 2 E11, and this is 1 plus 2 E22. Okay, that's something that this T1 ET1 is E11, T2 ET2 is E22. That's something that we have seen before. What about this part here in the numerator? This can be split in the sum of two results, T1 times 1, which is T1 times T2. So the product of T1 times this times T2 is T1 dot product, or scalar product, T2. What is the result of this? They are two orthogonal vectors. What is the dot product of two, or the scalar product of two orthogonal vectors? Is 0. They are orthogonal, it's 0. Okay? So this is 0. So this drops. So finally, here it comes T1 E T2. And T1 E T2, if you go back to that expression, and here you put 1, 0, 0, and here you put 0, 1, 0, the product of this times this being 0, 1, 0 is the second column, so the product of this times this gives this term here. So finally, just simple calculation shows that the numerator is 2E12, and the denominator is that one here. So we can say that the cosinus of that angle that was unknown, in fact, can be computed as the arch cosinus of twice E12 or EXY divided by this, which are 1 plus 2 EXX square root 1 plus 2 EYY. Just by some trigonometric issues, we know the arc cosinus of something is pi over 2 minus arc sinus of something. So finally, we can say that this angle can be written in that way. Why this? Because that's more comfortable for what is coming. Let's talk about the increment of the angle. So the angle that initially was pi over 2, finally goes to that angle. Okay? What is the increment of the angle? It's the difference of theta minus pi over 2. So theta minus pi over 2, this term goes to the other side, and this part here is the difference of theta minus pi over 2 being the difference, the original angle. So the increment of this angle is given by this formula here. That's the final result. So what is this formula saying? That if we want to know the increment, so an angle that, or two segments that at the reference configuration were oriented in the x1 and x2 directions, that is forming an angle of pi over 2. And we want to compute the increment, so how much has augmented this angle? I just have to apply this formula. Look that this formula has a minus in front. Never forget this minus. Okay? So the increment of one angle that at the reference configuration was pi over 2 and was formed by two segments oriented in directions x1 and x2 is given, or X, capital Y, is given by this formula. Look, what appears here? EXY. So that's the term that was in here. That term here, I mean, with the help of this term and this term, but this term here informs about the variation of angles. Variations of what angles? Well, the superscript says about what angles are we talking about. The angles formed by segments that at the reference configuration were oriented in the directions x and y. And if we know that, and by also knowing that, we obtain that the variation of this angle is given by this formula. Okay? This can be extended to the other directions and say that the component xz of the strain tensor, that component here, informs about variations of angles which are initially in the reference configuration segments placed in the directions x and z. So segments that are placed one in that direction and the other in that direction. And EYZ informs about the variations of angles that were placed in the reference configuration in the directions YZ. Okay? So, what is the final decision? Imagine that we are given a straight tensor. Imagine that we find that this term is 0. What can we say if this term is 0? That means that segments that at the reference configuration were oriented in the xy directions have an increment of the segment 0. So if they are orthogonal at the reference configuration, how are they at the present configuration? Orthogonal. So they don't change. The point to keep in mind is that if these strains here are 0, mean that the angle keeps the same, so orthogonal. If this value is greater than 0, what can we say? What can we say if this value is greater than 0? That means that this increment, you know, the sinus of a negative angle, keeps the sign of that, so finally this is positive. The final result, that being positive, that will be negative. So if that component of the strain tensor is positive, that means that the angle, the segments that initially were orthogonal to each other, then have closed. The angle has decreased, being that positive. That is something that sometimes you don't keep in mind, and that's important. So positive value of these terms here means that the angles along the formation tend to close. The original orthogonal angles, pi over 2, tend to close. And counterwisely, if these values are negative, that means that the increment of the angles after the formation are positive. The same about that. If these elements are positive, if any one of these is 0, that means that there is no unit elongation. So the length is kept constant. If they are positive, that means that the length in the direction increases. If they are negative, that means that the length in these directions are negative. So having a look onto the sign and the values of the components of the material strain tensor, we have an idea on how a given segment oriented in a certain direction or a given couple of segments oriented in the Cartesian directions have moved along the formation. This is synthesized here. Imagine that we have a particle P and through three other particles, Q, R, and S, which are placed following the Cartesian directions, like that. So we can consider this parallel pipette here, which gets deformed, and the deformed configuration to point P prime, Q prime, R prime, and S prime. These are not orthogonals anymore. So these angles that were orthogonal, this square root times one dot inside means that they are orthogonal. They are no longer orthogonal after the formation. These angles have varied. But if we know the component of the strain tensor, we can, so to speak, plot what would be the shape of this deformed parallelepiped here in the deformed configuration. For instance, this length would be that length, PQ. The length PQ prime will be the length PQ multiplied by square root of 1 plus 2xx. This length, the length P R prime, would be the original length multiplied by lambda 2, which is square root of 1 plus 2 EYY, etc. So the components epsilon xx, epsilon y, epsilon zz will inform about the increase of length of these three segments. The larger they are, the lengthier are the corresponding segments. And what about the increment of angles? The increments of angles depend on components exy, exz, eyz, in such a way that if exy is positive, that will mean that this angle, the angle of particle q and particle r, has what? Increased or decreased? Decreased, because of this minus sign. And if the value of exy is negative, that means that the angle has increased. So to speak, this figure provides an information of the meaning of every of the components of the strain tensor.